We studied one-to-one functions, and to understand what those are, we look at the definition. A function is one-to-one if no two elements of the domain have the same image. That is, whenever two domain elements are different, the range elements have to be different. So whenever x1 and x2, two x values, are not the same, then the two function values also cannot be the same. So here in this arrow diagram, you can see that the function g is not one-to-one because here are two different x values, 3 and 2, that have the same function value, 4. So we have g of 3 equals 4, and we also have g of 2 equals 4. And that just can't happen with a one-to-one function. What it means graphically is that if there are two different x values that have the same function value, so as in this picture, two different x values that have the same function value, so there's f of x1, that's the height, and there's f of x2, that's the height. The heights are the same, which means that a horizontal line crosses the graph in more than one place. And there are lots of places on this graph where a horizontal line will cross in more than one place. So what we have is this nice horizontal line test, which is a direct result of the definition. If two x values are different, the function values have to be different. If they are the same, then that means that there's a horizontal line that crosses the graph in more than one place. And so the horizontal line test is the test for whether a function is one-to-one. So it's easy to tell from the graph whether a function is one-to-one, provided you can draw the graph. So we have several functions here. The first one is the square root of x function, and we know what the graph of f of x equals, or g of x equals the square root of x looks like. It looks like that. It continues to rise throughout its domain, and we can see from the graph that no two points are on the same horizontal line. If you imagine horizontal lines crossing this graph, they will never cross the graph at more than one point at a time. So that function is one-to-one. On the other hand, the function h of x equal x squared minus 2x has a graph that is a parabola. And so that means we know this function will not be one-to-one. We should be able to think of two x values that give us the same function value. Well, let's think of what h of 3 would be. H of 3 is equal to 3 squared minus 2 times 3. 2 times 3. And 3 squared is 9, and 2 times 3 is 6, and 9 minus 6 is 3. So h of 3 is 3. Let's find another number that gives us 3 for the function value. So we want to find an x such that x squared minus 2x is equal to 3. So let's solve this equation. X squared minus 2x minus 3 is equal to 0. We can factor this. That'll give us x minus 3 times x plus 1 equals 0. So we see we have x equals 3, which we already knew, but the other value that gives that same value is x equals negative 1. So you see we have two x values that will give us the same function value. Let's calculate h of negative 1. H of negative 1 is negative 1 squared minus 2 times negative 1. Well, negative 1 squared is 1, and negative 2 times negative 1 is 2, and 1 plus 2 is 3. So you see we have two different x values, in particular x equals 3 and x equals negative 1, that are not equal, but the function values are the same. They're both equal to 3 when you substitute those x values into the function. They both make the function equal 3. So the function is not one-to-one. Now in class, I showed you how to complete the square on this function so that you could get the graph. So let's show again how to do that. To complete the square on this, you would simply have to think of what do you have to add to x squared minus 2x in order to get a perfect square. Well, you have to add half of the coefficient negative 2, which is negative 1, and then squared. Negative 1 squared is 1, so we have to add 1. But adding 1 changes our function, so we have to compensate for adding 1 by subtracting 1. Now we've essentially added 0. But we can now write our function like this: x minus 1 squared, by grouping together these three terms and factoring the perfect square, and then minus 1 because that's what we have left on the back end. Now we see that we have a transformation of the basic x squared function, 1 unit to the right and 1 unit down. And so when we draw that graph, we can see that where we started at 0, 0, we're now 1 unit to the right and 1 unit down, so we're now here. And our graph does something like this, and we can see from the horizontal line test there are lots of points on the graph that are intersected by horizontal lines in more than one place. So we see that that graph is not the graph of a one-to-one function. Finally, f of x equals negative 2x plus 4. That's just a line. I'm going to leave the details to you. We did this in class. You should be able to graph that line because you know the y-intercept and you know the slope. And once you graph that line, you should see, like all linear functions, that this is a one-to-one function. Now, the reason we study one-to-one functions, or one of the reasons, is so that we can use them to determine inverse of a function. It turns out that one-to-one functions are the only functions that actually have inverses. And so, if we can determine that a function is one-to-one, we'll know it has an inverse, and then sometimes we can find the inverse. Sometimes we can't. It just depends. So keep in mind the fact that the definition tells us that if f is a one-to-one function, then the inverse, f inverse of a y value, is equal to f, and that means the same thing as f of x is equal to y. These two are equivalent. They mean the same thing. So if you know this information, you can obtain that information. Conversely, if you know this information, you can obtain that information. And that's because, as you see in this little arrow diagram, that when you apply f to a function, you get y, and when you apply f inverse to y, you get back to x. So let's see what happens if we assume that our function f in these examples is a one-to-one function, and we know that f of 2 is 7. So think about the diagram. So here's 2, and we're going to do f of 2, so that's going to place 7 over here. So f of 2, when you do f of 2, you get 7. So what does that mean f inverse of 7 is? Well, when you do f inverse of 7, since f is the inverse of f, you should get back to 2. So f inverse of 7 is 2. On the other hand, suppose if you know that f inverse of 3 is negative 1, since this is f inverse, that means that you're in set B, and that's where the 3 is. So 3 is over here, and if you do f inverse of 3, you get negative 1. So negative 1 is over there. Now, if you do f of negative 1, since f is the inverse of f inverse, you should get back to 3. So f of negative 1 is 3. Now, the inverse function property is very important for verifying that two functions are inverses. So basically, these are called the cancellation properties. And if you do f inverse of f and get x, and also f of f inverse of x and get x, then the two functions are inverses. And if the functions are inverses, this will always happen. We'll use this in a few minutes, but right now we're first going to use a graph to find indicated values. So here we have f inverse of 2. Remember, f inverse of 2 means that 2 is in the range of f. The domain of f inverse is the range of f. So this 2 is in the domain of f inverse, but it's in the range of f. Where is the range of f? Well, the range of f is on the y-axis. So we find 2 on the y-axis, and here's 2 on the y-axis. And now we want to find the function value for 2. So we want to find where that 2 came from. That 2 goes with that point on the graph, which has an x-coordinate of 6. So f inverse of 2 is equal to 6. What about f inverse of 5? Again, the domain of f inverse is the range of f. So that means this 5 is in the range of f. So where's 5 on the range of f? Here's 5 on the range of f. So what's the function value? What's the number that we get, that we have to use in order to get a 5? Well, we go to the graph, we find the point on the graph, and then from there we read the x value. The x value is 3. So f inverse of 5 is 3. Finally, f inverse of 6, again, the domain of f inverse is the range of f. And so that 6 is in the range of f. So where is 6 in the range of f? 6 in the range of f is on the y-axis. There's 6. And the graph happens to go through that point because that's the y-intercept. So f inverse of 6 is 0. That's the x-coordinate of that point. Okay, the inverse function property is right here, the cancellation properties, and we'll use that to show that f, this function f, and this function g are inverses of each other. So in order to do that, we have to do f of g of x and show that that equals x. Well, that's f of x plus 5 over 2. And that means substitute x plus 5 over 2 in the function f wherever you see the variable. I see it exactly right there. So I have 2 times x plus 5 over 2, and then minus 5. Alright, so 2 times x plus 5 over 2, the 2's can reduce, that's just 2 over 2, and that's 1. So I get x plus 5 minus 5. Well, plus 5 minus 5 adds up to 0, and so I end up with x. So I just showed half of what I have to show. I also have to show that g of f of x is equal to x. So which g of f of x? That's g of 2x minus 5. And g of 2x minus 5 means substitute 2x minus 5 into the function g wherever you see x. I see it right there. So I'm going to put 2x minus 5 right there, 2x minus 5, and then I have plus 5, and then I have divided by 2. Now again, in the numerator, I have plus 5 and minus 5. That adds up to 0. That gives me 2x in the numerator over 2. And now I have 2 over 2 here. That can reduce, and that leaves me with x. And so I have showed that f of g of x is equal to x, and g of f of x is equal to x. And so therefore, by the inverse function property, f and g are inverses of each other. So how do we find an inverse function? In that example, we were given that the two functions were inverses. How do we find the inverse of a function? We find the inverse of a function by realizing that a function and its inverse are just two functions whose ordered pairs have been reversed. And so the first step in finding the inverse function is to interchange the variables. Well, remember that f of x is the same as y. So we start by saying y equals 2x plus 1. Now we interchange the variables, which means we substitute x for y and y for x. So technically this is the inverse function, but we like to have it solved for y. So we'll solve this for y by subtracting 1, x minus 1, that equals 2y, and now divide by 2. X minus 1 divided by 2 is equal to y. And that is the inverse of f. So f inverse is of x is x minus 1 divided by 2. For the second problem, I have a small typo on the notes. We should have the added provision here that x is greater than or equal to 0. Without that, we won't be able to find our inverse because 4 minus x squared by itself is not a one-to-one function. But if you restrict the domain of 4 minus x squared to just those x's that are greater than or equal to 0, you do have a one-to-one function. Let's turn to the graph and see why this is the case. So remember, I should have the added provision here that x is greater than or equal to 0. In general, if you graph 4 minus x squared, you get the parabola. Well, let's see how that looks. If we graph 4 minus x squared, let's start with x squared. The graph of x squared looks roughly like that. Okay, so now first thing we have to do is the minus of x squared. So the minus of x squared is a reflection across the, let's see, it's a reflection across the, every function value, every y value is opposite, so it's a reflection across the x-axis. So this graph will be reflected across the x-axis because every y value, every x squared value will become the opposite. Every x squared value will become the opposite. This one will stay the same, and so the reflected graph is going to look like that. So minus x squared looks like that. And then finally we have to add 4. 4 minus x squared means that we're going to shift vertically 4 units. And so the graph is going to go through 4 on the y-axis, and it's not too hard to see that the x-intercepts here are plus and minus 2. But remember that we restricted the domain in the original function to just those x values greater than or equal to 0. So the original function is actually just half of the parabola right there. And that's good because that half of the parabola is a one-to-one function. Now when we do our first transformation, that part of the parabola goes into the fourth quadrant. So our second graph for x is greater than or equal to 0 becomes minus x squared right there. And then our next transformation shifts that graph up 4 units, and so that branch of the parabola is going to end up being right here. So you see just the red part is what I have here. I'm only using x's greater than or equal to 0, and with that restriction I do have a one-to-one function. So then I want to see what the inverse function is. So let's calculate what the inverse function would be. The inverse function, I'll do it down here. We start by saying y is equal to 4 minus x squared. So now we're going to try and solve for, we can solve for x. So we'll get, put x squared on the left side and bring the y over here. I'm going to have a positive coefficient for my x squared term. Now, since I know that x is greater than or equal to 0, when I take the square root, I know that x right here is greater than 0. Therefore, I know that I want the positive square root of 4 minus y. And now I can interchange my x and y variables and get y is equal to the square root of 4 minus x. And so the inverse function is a square root function where the x values have to be less than or equal to 4. Well, here's where x equals 4 on my original graph. And so the x values have to be less than that, so the domain goes this way for the function that I'm looking at, and it's a square root function. And when x is 0, y is 2 in the inverse function, so that means that it goes through here on the y-axis, and it starts here on the x-axis, and it's a square root function, so it looks like that. So there's the graph of the inverse function. The blue is the graph of the inverse of the red function. Remember, we had to limit the domain of 4 minus x squared to just those x's greater than or equal to 0 so that we end up with a one-to-one function. The last example on this page is the graph, or to find the inverse of the function f of x equal to x over x plus 4. So let's go ahead and do that one. X over x plus 4 is equal to y, so y equals x over x plus 4. So we can either interchange the variables now, or we can solve for x and then interchange the variables. It doesn't really matter which way you do it. It amounts to the same thing. Let's interchange the variables. So let's change y to x, and we'll change x to y. Y over y plus 4 is what we get here. Now we're going to solve for y. So we have to multiply by y plus 4. So x times y plus 4 is equal to y. Now do the multiplication on the left-hand side. That's just the distributive property. xy plus 4x equals y. Remember, we're solving for y, so that means we want all the terms that have y on the same side of the equal sign. So this term and this term should be on the same side of the equal sign. So we'll do that. We'll come up here and do that. So we have xy minus y, and we'll put 4x on the other side. That gives us a minus 4x. Now we're going to factor the y. So we have y times x minus 1 equals negative 4x, and now we just have to divide by x minus 1. So y is equal to negative 4x over x minus 1, and that's our inverse function. This is the inverse of f of x. So f inverse is equal to negative 4x over x minus 1. Okay, so knowing how to sketch the graph of a function and use that to sketch the graph of the inverse function is a useful skill. So here we have f of x equals the square root of x plus 1. So we're going to draw that graph using what we know about translations. So the square root of x plus 1 is a translation of the square root of x function. It's shifted 1 unit to the left. So that means that the x-intercept is at negative 1, and the y-intercept is at positive 1. That's what you get when x equals 0. So these 2 points, that one and that one, are the 2 intercepts, and it's a square root function, so it does something like this. So that's the graph of f of x equals the square root of x plus 1. Now, to use the graph to sketch the graph of f inverse, you remember that in f inverse, the ordered pairs are just reversed from what they are in f. So the ordered pairs are opposite. So here we have, what is this? This is negative 1, 0. So f inverse is going to have 0, negative 1. So 0, negative 1 is right here. Similarly, this point is 0, 1. So f inverse is going to have the point 1, 0. So it's going to have that point right there. So these 2 points are going to be on f inverse. So what you see is that this point moves to here, this point moves to here, and what we're going to end up with is a graph that looks like this. That's the graph of the inverse function of the square root of x plus 1.